So I'd like to tell you a little bit about our work on CheriABI. So this is collective work, a large number of co-authors, especially Simon Moore, who spoke yesterday on the topic of the CHERI architecture, also our collaborators at SRI and the University of Cambridge. What I'd like to do is tell you about CheriABI. So we spent the last 7 years developing architectural extensions for security, and this is inevitably a hardware-software project. We have to change the software to use these new features, and so this talk will say a little bit about the process of how we did that and the kind of benefits that we see. So first of all, I will tell you a little bit about the CHERI architecture. I'm going to assume that many of you were at Simon's talk, but I'll refresh you on a couple of bits of it. Talk briefly about our methodology and approach, and then talk about the implications themselves. So what is the impact on software design and security? I was going to mention, if you want to learn more about the CHERI architecture, you can go to the website, chericpu.org, and also we have our instruction set architecture, which is not just a guide to the architecture itself, but also the design of the architecture and why we went about the way we did it. So maybe we should sort of visit the high-level CHERI software protection goals. So we're interested in protecting C and C++ trusted computing bases, or TCBs. These are the low-level software packages under which managed languages and higher-level applications run, whether it is your operating system kernel, your language runtime for Java or JavaScript, your web browser, and so on. On the whole, in this talk, I'm going to be talking about spatial memory protection and pointer integrity protection. These are going to be the kind of protections that prevent the successful exploit of buffer overflows and control flow exploit techniques and so on in C language stacks. But we do some other things too. We're able to provide foundations for temporal safety, such as reliable and accurate C language garbage collection. We can provide tools in the instruction set that assist in the implementation of higher-level managed languages that do have type safety and memory safety as part of the design. For example, we can provide the safe interaction with native code, such as in JNI, and we can also provide hardware assistance for dynamic checks that are used in higher-level languages, such as bounds checking in Java. We also support scalable in-process compartmentalization. This is the ability to have fine-grained sandboxing inside of processes with substantially better performance properties, actually orders of magnitude better performance properties than current designs. In this talk, I'm going to talk primarily about the first couple of topics. So I will remind you perhaps a little bit about architecture and how attackers see the world. Today's architectures are not designed around a principle I think David Wood mentioned in the first talk, which is the principle of least privilege. Principle of least privilege tells you that you should design software to use and have as little privilege as possible so that when it is inevitably compromised or abused in some form, it limits the damage that can be done. And so when we talk about architectures lacking least privilege, what we mean is that there is an excess of privilege in the representation of the program, and the attacker is able to exploit that excess of privilege. So in a classical buffer overflow attack, which you're probably familiar with, but I'll remind you nonetheless, we allocate some string on the stack. We have a pointer perhaps to the base, and then a length, and software is managing those bounds, managing the indirection implemented through instructions. Our compiler helpfully puts the return address slightly above the buffer. The attacker exploits a bug in the application's handling of the bounds, overwriting the return address. The attacker's value gets propagated into the return address register, and then finds itself in the program counter, at which point the attacker now has the ability to control execution of the program. And in the historic version of this attack, we would inject some code into that buffer, and we just run the code that we'd injected. More recently, we have preventions to prevent people from executing data as code, but that's OK. We'll just reuse the code you have in your address space already. We'll borrow bits of your libc or your application itself, and this is well understood technique, sort of return-oriented programming and jump-oriented programming. So we could ask, why is it that these behaviors were things that were permitted at the architectural implementation of the software, given that the C language doesn't really require us to allow the programmer to overwrite target buffers, corrupt and manipulate code pointers, and then to execute data as code, and so on. And the answer is, if we took these privileges away, we would not eliminate the bug would remain, but we would mitigate the vulnerability. We'd make it harder for the attacker to use this vulnerability to gain privilege in the system. And the somewhat sad news about the current state of affairs is that memory management units, which are roughly the state of the art in memory protection across the vast majority of systems, aren't really designed to do this. And so CHERI is intended to address this. So if we think for a moment about the behavior of pointers today, pointers are implemented as integer virtual addresses. They are an integer that you load and you manipulate and you index using your load and store instructions. On a good day, they point into a memory allocation or maybe a memory mapping provided by your kernel. And what we like to do with pointers is derive other pointers from them, and we do this through integer arithmetic to move pointers through buffers and around the address space. Once in a while, we will dereference these pointers by jumping to them and fetching instructions or loading and storing data. Today, there is no integrity protection provided for these. They can be injected, they can be corrupted, and so on. They're subject to arithmetic errors. Often these come in the forms of failed bounds checks, but also wraparound and so on, which can be exploited by attackers. And it's quite hard to get these checks right in the C programming language. They're also subject to inappropriate use, which means pointers may be used for things that you don't intend. A pointer into a stack might be used to refer to heap memory, for example. And I guess the point of view from attacker is that code and data pointer manipulation is a great way to exploit systems. You gain a lot of control by manipulating references to code and data. Oftentimes this leads to arbitrary code execution, and that is a very powerful attacker model. There are, of course, other attacker models that have to do with vulnerabilities in application logic, but why would you even go to the trouble to find those if you can simply own the system and run any code you want to? So what we do in CHERI is we try to impose some stronger properties on the implementation of pointers. And you'll have seen this picture in Simon's talk yesterday. If having heard what I told you about pointer derivation and pointer manipulation, you start off with pointers to the address space as a whole, into mappings, and then you subdivide them as you perform memory allocation. Some administrative metadata breaks up and subdivides the total address space, and then we derive pointers and pass them on to the next level of abstraction. So CHERI brings integrity and provenance validity. Integrity means that you can't corrupt the pointer and have it remain valid for dereference. Provenance validity is an inductive property. It says that your pointer has come from someplace via a valid set of transformations. I'll say more about that in a moment. But this prevents attackers from injecting and sometimes from misusing pointers inside the address space. Bounds checking is a familiar technique. Bounds prevents you from using a pointer to one allocation to refer to another. And we actually have quite a strong form of bounds checking. We tie it to a notion of monotonicity. Monotonicity says that once you've narrowed the rights on one of these pointers, you can't then restore them to more broad rights. So this prevents escalating privilege associated with a pointer. And then because pointers don't just refer to data, they also refer to code, we have a permissions mechanism that allows us to constrain what the hardware is willing to use a pointer for. So overall, provenance and monotonicity are going to limit whether or not a pointer can be dereferenced. And if we have that, we have this inductive set of rules that say valid pointers are simply prior valid pointers that have been transformed in a valid way. So the hardware is going to maintain these invariants. You cannot generate a pointer that you can dereference in the hardware unless it's been suitably derived according to the rules. And this is going to let us do things like prevent network data from being interpreted as a pointer. You simply cannot inject a pointer into the system via normal data. We then use bounds and permissions to constrain how the pointers are used, and this is going to be managed by software. The goal is to minimize the permissions and the bounds, because every time you do that, you limit the ability of the attacker to exploit the existing configuration of the system in order to gain privilege. So for example, we can prevent pointers that point to one allocation from being misused to point to any other allocation, even if we're able to manipulate the pointer arithmetic that goes on around that pointer. And once you have this functionality, then you can build higher-level software models on top, such as fine-grained memory protection or compartmentalization. So in CHERI, just to remind you, we're going to take our 64-bit virtual address, which is what we think of as the pointer today, and we're going to extend it in various ways to add protection features. And I'm going to describe quite a large object, a 256-bit object, but as Simon mentioned, we have an efficient implementation that allows this to be done in 128 bits. So we will now start adding bits and see what happens. So the first thing we do is we extend the pointer with an in-hardware tag that's going to track the provenance, validity, and integrity. If you want to dereference a pointer, then it has to have the tag present. If the tag isn't present, we're going to throw an exception. So we're not able to dereference it if it's been tampered with. If it's overwritten in memory, let's say the pointer, the tag is going to be automatically and atomically cleared. So if there are race conditions in the updating of pointers or attacks involving buffer overflows and so on, we're able to catch that and prevent dereference. The bounds associated with this pointer are going to give us lower and upper restrictions on the memory that can be accessed. It's not the pointer can't point outside the bounds, you just can't dereference it outside the bounds. We have permissions to limit the operations, as I mentioned. We have some other features. I'm not going to go into detail on those today, but these relate to the implementation of fine-grained compartmentalization. We can have opaque pointers that cannot be dereferenced, whose fields are immutable, and that allows us to refer to other higher-level software objects rather than hardware interpretations of pointers. So we can reuse these protections for software-defined objects. And what I won't do then is tell you about how 128-bit capabilities work or how sealing works. So the CHERI project has been now going on for just under 7 years. We have a portable CHERI protection model. This is abstract. It is architecture independent. We found that it can be mapped into several architectures. This affects how we design software. We program to the protection model, we teach the operating system about it, and so on. And one interesting thing we've learned is that we can really write portable CHERI code that is not specific to the MIPS architecture, which we designed it for originally. Using that model, we then build a specific instruction set architecture. We have a set of extensions to 64-bit MIPS called CHERI MIPS. We have a written specification that you can download. We have formal models that we use to reason about the instruction set architecture. We have a fast instruction set level emulator. We also have an implementation in BlueSpec System Verilog, which is multi-core, relatively simple pipeline processor, enough for us to reason about the impact on pipeline structure, critical paths, and so on. And then we have a large software corpus that we've ported on top of that, and that's primarily what I will talk about for the remainder of this talk. And of course, we perform evaluation to ask questions about protection, to learn about the impact on compatibility and security, and so on. And we do that over and over again because it's hardware-software co-design, and the chances of getting it right the first time are pretty low, and we say that from experience. So what are CHERI's implications for software? Well, the first thing is we're providing an architectural memory protection primitive. Primitive doesn't constrain how it is you choose to use it. You just use it in different ways. So as software authors, we can exploit CHERI in different kinds of ways. If we want to take advantage of its provenance validity, we have to know where pointers come from. In particular, we have to ensure that they come from somewhere sensible. If we're going to enforce integrity on pointers, we have to know that transformations of pointers in our software runtime environment don't mess with the integrity. They don't do things that would violate the architectural rules. If we're going to have bounds and permissions, something needs to originate those bounds and permissions. And if we're going to enforce monotonicity, we want to know that software actually uses pointers in that kind of way. We can also implement software compartmentalization, which uses these same underlying primitives, but as I mentioned, another talk. You'll have seen this picture also from Simon, looking at the kind of scope of ways that we can apply CHERI capabilities. We can focus on compatibility without very much protection benefit, or we can slide to the other end of the spectrum, lots and lots of protection benefit, but maybe reduced binary compatibility or perhaps source code compatibility. So we're able to run unmodified code. We're able to lightly modify code. There are various techniques we can use to make limited use of capabilities. For the purpose of this talk, I'm interested in pure capability code. This is code where we've taken every virtual address, every pointer, and we've replaced it with a capability to see if we can get the software model to work. This will offer us the strongest protection. And we have a Clang and LLV implementation that can target all three of these modes. So if we want to move from this hybrid capability code, which is where we've done much of the research on CHERI over the last few years, then we need a new runtime environment. The hybrid capability code takes advantage of a process on top of Unix, which is basically a MIPS process. Most pointers are integers. So if we want to run capability-aware code everywhere, then the kernel is going to have to understand how to interact with it. The pointers that go in and out of the kernel are going to be capabilities. This is what we've been working on for roughly the last 2 years, looking at high-level software development on CHERI. And the goal here is that every pointer and every virtual address, and by implied virtual address, I mean things like return addresses or vtable pointers, everything in the runtime environment is going to be strongly protected. So we want to do this at scale. First, we want to know, can it work at all? But then we have some specific hypotheses. For example, we want to know that all these pointers, implied virtual addresses, either do have valid provenance or that we can ensure they have valid provenance. If they don't, then the program will crash and burn almost immediately. Right. On bounds and permissions, we want to know how small you can make them and still have your software work. The smaller we can make them abstractly, the better the protection properties. Monotonicity seems like a sensible idea. It prevents privilege escalation, but does it interfere with the actual operation of software in practice? And then on performance, can we get sensible performance overheads? We're looking for a couple of percent, maybe in a worst case scenario, sort of 5 or 10%. We're not looking for an 100% overhead. If we want that, we can run existing software bounds checking based techniques. So in terms of methodology, first develop the compiler suite. OK, we did that. Then develop a set of OS extensions to allow us to run this pure capability code in the first place. That's been a significant focus and is something that's now pretty much come to fruition. We then want to adapt a complete set of applications to run on top of it and exploit the features and look at their interactions. Done that. We then want to measure a whole ton of properties about it. And it turns out that because CHERI exposes more application semantics of the hardware, there are aspects of software behavior that we can study much better on top of CHERI than on top of conventional architectures, which is quite convenient given that we have all these questions. And then we revise all of these aspects as we make improvements. We figure out C compatibility behaviors or OS behaviors. And we do it all over and over again, and we did. So what do we have to do in order to get to a complete CHERI-aware application user space? We need a set of system libraries. We need runtime linkers. We've adapted programs like SSH and OpenSSL, simple programs like BinEcho, and then sort of surprisingly complicated programs like OpenSSL. We've also ported large-scale applications like Postgres, Nginx. We're currently working on WebKit, which requires a slightly more mature C++ environment than we currently support on CHERI. We then want to go around and find all these pointers, and we want to ensure that they have these properties. So we're going to originate all capabilities in a small number of root capabilities provided to user space. User space can't just make these things up. It has to get them from somewhere, and the kernel is where it gets them from. And then we're going to modify our compilers and our allocators and our runtimes to refine the bounds and the permissions wherever possible, because we want to minimize these writes. Sometimes, once in a while, we're going to find there's a trade-off between minimizing privilege or implementing monotonicity and API conformance. So to give you an example, the realloc function, you malloc some memory, you go back some memory with some bounds, and you now want to trade your pointer in for some more memory. And realloc is very clever. It says, oh, actually, if there's enough space off the end of your allocation, I'll just return the same pointer, and you'll know to use it. If I have to go find more space, I'll copy the data and return a new pointer. So that's interesting because realloc is now going to return possibly the same pointer, but with more writes associated with it. In CHERI, we associate bounds with pointers, so how do we make that be bigger? Likewise, mmap and mprotect. Mprotect might turn your pointer from being readable and writable to executable. That is a non-monotonic operation. And mprotect does not return a new pointer. So we have to have a pointer perhaps that has more writes, or we have to change the API. So there's a tension between compatibility and privilege minimization. So at a high level, what do we have to do? Well, to get to the point where we could run hybrid code, which is selected capabilities, we made a bunch of changes to operating system kernels. We taught it how to maintain tags in virtual memory. We taught memory allocators to set bounds and so on. From that baseline, we had to do a lot more work. We had to teach the kernel how to have a system call interface, how to deliver signals, the initial process setup. So not only did we have to parse in capabilities, but we had to limit their bounds as much as possible. And sometimes this means changing things around the layout of the process so that you can minimize bounds further. We modified the runtime linker. We had to review and adapt a lot of pieces of software, but I'll show you how much. So the inevitable question when we say things like changing the semantics of C pointers and imposing monotonicity is, oh, I know someone who does some terrible things with pointers. That's obviously not me. So C programmers know that pointers are integers, and they're really quite sure about this, and their software reflects that belief. We know that recent compiler optimizations have been very upset about those conclusions, and one of the interesting things we know is that it's not possible to implement malloc according to the C standard. It's just objects are part of the C standard, so you can't write your memory allocator in it, which is a shame, because that is how we write memory allocators. Also, we now have this other stuff that comes with a pointer. It isn't just an integer virtual address. So we have this out-of-band metadata, the tag. We need to not lose those in places where we would prefer not to, such as in memory copies. And then we have this in-band metadata, which made our pointer annoyingly bigger, but also causes it to be a different width than our virtual address size. What else goes on? Well, we require quite strong alignment of pointers, strong enough that sometimes we find pieces of software that don't like that. For example, hash tables that do not use pointer alignment for pointers. This turns out to be more common than you would like, so I have to change that software. We need memory copies to preserve tags, because people like to copy pointers. They also like to sort pointers, it turns out, so your sort routine had better preserve tags. Slight surprise, it makes perfect sense now. On the whole, pointer arithmetic just works, which is great. And the stupid things people do with the lower bits of pointers also tend to just work. They're just manipulations on the virtual address. That's fine. But casting back and forth with integers got very exciting. So if you, for example, cast one of these wide fat pointers into an integer that definitely doesn't have room for that metadata, we refer to this as a sort of a provenance discarding cast. You've turned it into a virtual address. You're welcome to look at it, but good luck dereferencing it. On the other hand, in our environment, we're allowed to change the size of basic types. It's a new ABI, so we can have an int pointer t that is preserving. And this, in general, works. And we found that, somewhat to our surprise, because most C programmers don't understand what int pointer t is for, most C programmers use int pointer t correctly. This is shocking. There are some other surprising things about C, or maybe they're not so surprising. There are APIs where people are kind of confused about whether they want a pointer as an argument. So ioctl takes this thing, which is sometimes an integer and sometimes a pointer, but there was no int pointer t in 1974 when the interface was introduced. So we need it to be int pointer t, because we need the kernel to be able to take both there. There are all kinds of cool techniques like nanboxing that allow you to take bits and pointers that happen to align with a not a number bits and floating we generally don't support those very well, but we tell you it's great because you can now tell if something is a pointer because it has a tag. And then we find these interesting things such as monotonicity changing the semantics of APIs. So you may not think of free as being non-monotonic, but when you free something, you return it to the memory allocator. It has to go find the metadata. And the usual place to store it is just outside the bounds of the memory allocation. So we generally encourage re-derivation of capabilities there. So our JMalloc is slightly tweaked to know how to do that. And then there's some really mind-blowing things. So you get back a pointer from realloc. It has different bounds, but the same virtual address. Is it the same pointer or not? Some discussion is required. And then some surprising and cool but very scary things. If you want garbage collectible C, yes, we can do that as long as you don't allow virtual addresses outside of tagged memories, which changes integer interpretations further. This is the bit where there's probably the most tricky set of trade-offs. We may end up in a place where you pick, do you want garbage collectible C or not? We'll find out. And then some really obscure things. It turns out people like to take functions that accept variable arguments, and then they like to pass them via function pointers that don't have variable arguments and then call them. And if your ABIs differ, bad things happen. So we want to evaluate compatibility. So what did we do? We took the complete FreeBSD operating system. We took all the libraries and the applications. We took major applications like Postgres, and we measured how much work it was to change them. So, and it did require some changes for things like, oh, you're casting things in ways we don't quite like, or you assume things about the alignment of pointers or the integrity of pointers and so on. But relatively few things. So only 34 of the program, 824 programs in FreeBSD actually had to be changed. Although 28 libraries sounds like a lot, you realize a few of those are things like runtime linker-related libraries and memory allocators. So those are inevitably changed, which meant that about 200 out of 20,000 C files and headers had to be changed, which is not so bad. And the good news is that we have quite a few compiler warnings, which will help us identify code that is suspect in our environment. We also want to know that software works when you're done. So we run the BSD test suite and application test suites, such as the Postgres test suite. These generally work out pretty well. There are some areas where we fail. In fact, we found that the MIPS test suite in some places runs slightly better on CheriABI. It turns out MIPS is not enormously well tested with the FreeBSD test suite. Right now, we're not running our test suite with dynamic linking, and this explains a number of the failures, but we do run into other problems. We've also found several bugs in the test suite due to buffer overflows and corrupted pointers and so on. Thinking about protection, how do you evaluate protection? Well, you want to do an adversarial analysis. You want to do a historic analysis, look at past vulnerabilities and so on. So the good news is we do eliminate, by definition, a bunch of attack techniques, such as ROP and JOP. If we look back at past buffer overflow-related vulnerabilities, not just memory corruption, but also data leakage like Heartbleed and Cloudbleed, no problem. But also some interesting ones. So Stack Clash, which was announced a couple of months ago, is one in which your stack pointer is accidentally reused as a pointer into the heap. For us, this is a violation of provenance and an inappropriate use, so we can pick that up without a problem in the CheriABI environment. We can also run test suites, such as the buffer overflow-related test suites, and we find that we perform very well there. So if you compare us to Address Sanitizer, which is a reasonable state-of-the-art of debugging bounds checkers, we come in about the same place. We catch a couple of things that they can't catch. And then, I guess, a really critical question I'm going to now is, when we look at existing exploit techniques and existing known vulnerabilities, we have to think of it from the perspective of a CHERI-aware attacker. Right? We have to think about new kinds of exploit techniques, and we're starting to do that now. So I just want to mention a couple of minor things, such as the kinds of ways we can analyze software. So CHERI is quite neat. The hardware is aware of things that are pointers, and it will provide that information to you. We can find pointers in registers and in memory. This is why we can garbage collect. But we can also get extremely detailed execution traces out of the back end of QEMU or an FPGA implementation, which means that we can then analyze all pointer manipulation and use. So for example, we can construct a graph of the provenance of all the pointers and analyze it against the structure for binary and ask, are we getting the right bounds? And we can plot these kinds of things. So here, I just briefly mentioned in this sketch, horizontal axis is the virtual address space. Vertical axis is the passage of time in roughly cycles. And then we can look at where bounds are set. So the horizontal lines are bounds being set during memory allocations or pointers taken to stack variables. And we can visually inspect and understand every one of these behaviors. We can also do some quite interesting things in terms of looking at rights refinement, where data capabilities and code capabilities are leaked to, what capabilities remain on the stack after stack memory has been freed, and we can decide about trade-offs on memory clearing or temporal techniques. A couple of other things we can do. Once we have these traces, we can gather information on the bounds being used. So this is a CDF. So if you look at horizontal axis, this is the size of pointer allocations taking place in memory allocators such as the stack and the heap. The vertical axis is the percentage of capabilities allocated by some particular size. So what we want to do in general is, and these lines are different executions of programs with different bound setting policies, such as does the OpenSSL allocator set bounds. We want to push these lines up into the left-hand corner. We want as many bounds to be as small as possible. And if we're sort of off to the right-hand side, we discover applications are using very loose bounds, and they could perhaps be tightened to reduce the amount of privilege and try to prevent exploit techniques from working. So we can look at this to understand compiler behavior, application runtime behavior, and then we can look at these temporal aspects in terms of data leaks and capability leaks. Just to wrap up, we've spent quite a bit of time learning the hard way about why our software is designed the way it is, because we've been questioning the design choices of all of that software, aspects of runtime linkage and memory allocators, the construction of software at a very low level. In general, when you have these new primitives, it's quite hard to tell what they could be used for, and there are many different usage patterns. So trying to come up with new conventions and decide what they're good for and what the best applications are is quite challenging. It's particularly challenging because once you have these primitives out there and you don't have the opportunity to change them, people will be constrained in what they can do with them based on the design choices you made at the time of creating them, whether it's compatibility behaviors or performance behaviors or the effectiveness for security. And the best way to validate this stuff and refine it is to do the whole stack. What have we done? Well, we created a process environment in which all code makes use of capabilities. This provides us with very strong enforcement of properties that generally come out of the language model, not what we generally compile out of C, but information that is often available in C. It seems to provide pretty good compatibility, strong protection, and although I've not talked about performance, you'll have to take my word for it that it comes with reasonable overheads. And there are some interesting questions that come out of this. I mean, the architecture with CHERI is much more aware of the structure of software because it's enforcing that structure. And we have to ask the question, are there other benefits that could raise? For example, if we expose more information, can we teach pipelines or prefetches or other aspects, cache behaviors, to take advantage of that knowledge to improve performance and not just security? So I will direct you at our website, and thank you for your attention.
Thank you very much.